I'm going to just basically turn it over to our speakers, Kate Sweetland and Darryl Hwang, on standardized radiomic image feature calculation. I think I got through that. Here you go.
Thank you very much.
Hi, thanks. So as was announced, a standardized radiomic image feature calculations. And some of you might be wondering what radiomics is. So we're actually talking about medical imaging, so the field of radiology. And there's been a current trend in medicine to add the word omics at the end of every new technology that can be unveiled under the sun. So there's lipidomics and genomics and proteomics and now radiomics. So what is this? Let's talk a little bit about what you probably, anybody here do radiology or work in the radiology field at all? Anybody here has had an MRI or a CT before? Okay, so let's explain a little bit about what the practice of radiology really is, okay? And so it is a growing field insofar that we are planning on imaging you before actually doing things with you nowadays. In previous generations, a lot of this was reserved because the equipment was very expensive. It's still fairly expensive, but we didn't have the technology we have now to really peer inside the human body at the detailed levels that we do now. And what we found is it's better to look before cutting you open, right? And that's actually a big shift in the way medicine is practiced in the last 30 years. So I'm going to take off these glasses. I brought the wrong set. What we're talking about here in terms of radiology are the modalities that include X-ray, CT, MRI, PET, and other ultrasound can also be a modality. When we're talking about medical images, it's basically any image that's derived from scanning the human body. And one of the interesting things is that most imaging that is done on the human body is actually just a grayscale image of some sort on some kind of dynamic scale. And so we'll get a little bit more into that. Now, this is a kind of a surprising number that we found is there's 3.6 billion X-rays taken every year. And if you can just think about how much data that is. And keep in mind, most of this data, most of these images are just looked at and used qualitatively to diagnose either something like pneumonia or a broken bone, and then just left and not done anything else with. So what are we talking about? So there's a variety of different types of data here. X-rays are just two-dimensional images. Then we have three-dimensional images like CT and MR. CT and MR, three-dimensional images, are actually kind of rare. The only other example that we found of 3D imaging is actually used in seismology, in looking at how seismic waves propagate through soil. So it's kind of a weird field because most of the image processing techniques that have been invented are either for video or for are still images. So adding that third dimension is actually a significant change. And in addition to that, when you add the fourth dimension, which is how do these three-dimensional structures change with time, it becomes even more complicated. So let's talk about the sort of an elephant in the room in the medical community is what is actually the radiology workflow. You basically go and you scan the patient. That scan is reconstructed on the scanner. It's not the raw data that you get. And for those of you that do any kind of data science, you kind of crave that raw data. But what we get in medical imaging is a reconstructed data from a proprietary reconstruction algorithms that we can't actually access because those are trade secrets by the companies that invent these machines or that manufacture these machines. That image is then just given to the radiologist, and in general, the radiologist might do some little measurements, but most likely they're just going to do qualitative assessments. They're going to look at the image, dictate out their impressions of what's going on, and that's the majority of the radiological practice as we do it today. And then finally, that diagnosis is shared with your referring physician, and they will plan your treatment off of that impression and that summary. So radiology, very user dependent. If you get a diagnosis that is very severe or that is, that you're questioning, get second opinions. That's all I'm going to say about that. That's something that you should always, it's very user dependent. Again, it's a qualitative assessment most of the time, not quantitative. And then finally, it relies really on the experience of both the person conducting the study, which is probably a tech of some sort, a sonographer or a radiology technician, and the ability of the radiologist to interpret those images. So lots of things that can result in human interpretation and thereby human error. And then finally, radiologists are trained to work at speed. There is a growing trend of increased number of reads per day. And so the number of minutes that a radiologist can spend on any given study is smaller, in addition to the fact that there are more images being presented. Because as we get higher resolution images and thinner slices, there's more images to go through. So all these little facts. So radiologists are trained to find differences when looking at images. And they're trained very specifically for specific reasons. So if you tell somebody, hey, we're looking for lung cancer, and you give a radiologist a scan like this, they will be able to spot the cancer, which is, let's see, there we go, right there. Except when you show them an image like this, there is an inattention bias in that if they're not looking for it, they might not see it. For example, most of the radiologists shown on this, 83% of them, didn't notice that there was a gorilla implanted in the image. That shouldn't cause you too much concern considering they did find the cancer, which is what they were looking for. But again, they didn't find the gorilla, which, who knows? So why do we want to talk about this? Because we want to talk about radiomics. And what radiomics is basically a field that started roughly 10 years ago, a little bit more, maybe 15 years ago. And it's come with the advent of computing power. And also the high resolution scans that are available in medical imaging. And so like I said, it started around 2012, or at least it was quoted around 2012. I technically have been working on this since 2008 or so, so I'm ahead of my time. I think that's the take-home message there. And then, so one of the issues is that there's a lot of these tools that are being developed, and we're trying to assess how to use these tools. Because the entire idea is how do we turn these images that are digital data and try to extract metrics that are quantitative and then also useful. Just because it's quantitative doesn't mean it's useful. So we're looking at that. And then the entire idea is to generate these signatures of certain things like disease or normality or pathology that can be associated with looking at the images on a higher level than being able to spot the differences, which radiologists are well trained to do right now. So these are subtle things that might not be able to be discerned by the human eye. Like one texture analysis of an area is a little bit fuzzier than another, or there's a slight shift in contrast enhancement. These kind of little subtleties, computers are great at extracting out, but humans don't necessarily are able to see that very clearly. And one of the biggest problems that we have in radiology is because a lot of the stuff we do is qualitative, how do we generate, or how do we leverage machine learning? How do we leverage AI and all these nice tools for data analysis? We need robust statistics to feed these models, and this is one of the ways that we can start heading towards that direction so that we can use big data analysis with medical imaging. And we'll just go through really quickly the workflow. We talked about patient scanned, and then there's a reconstruction. For the radiomics workflow, we take that reconstructed image, and what we can do is then start doing things like image segmentation, meaning that we pick the area that we want to look at. For example, we want to look at a tumor or an organ. that doesn't just magically separate itself. How many people here watch TV in terms of like some medical show ever, like Grey's Anatomy or House or ER, any of those shows, right? What they like you to believe is that once it's scanned, everything is just parsed out, and there's a magical 3D image that appears, and everything is done by the surgeons, which none of that's true. All of this is actually still in the level of somebody has to do the work, somebody creates the 3D model, somebody segments out each of the individual sections. From that ROI, region of interest that we create, we can calculate quantitative metrics. And in this case, we're talking about our radiomics metrics. And then we can take those metrics and then we can try to compute baselines, or we can compare them to baselines that we've previously calculated. And that differs from our normal workflow, because normally that image just goes directly to the radiologist in red. But if we do this entire pipeline, we can give our radiologist more information and hopefully in the future make this a much cleaner and reproducible setup. And then finally, the prognosis. So I'm going to turn this over to my co-presenter.
So prior to IBSI, when we were calculating this radiomic data, it was primarily from in-house algorithms. So there wasn't really a set standard for how to calculate these metrics, which metrics to calculate, and this led to a lot of confusion, especially when arbitrary statistical decisions were made. There are 3 different ways to calculate entropy. There's a lot of different ways to slice up 3D space, especially because CT and MR data is different than regular 2D image processed data. By adding that 3rd dimension, figuring out when and how to average was difficult. And like when we're looking at measures of central tendency, we can have the mean or the median, and technically they're both the middle, but deciding which one to use, while it may be arbitrary, becomes a difference that propagates when we're trying to compare across different centers. So when we choose different formulas and try and say it's the same thing, we're all speaking different languages, though we're all trying to levy math to analyze these medical scans. And which features were calculated was also not consistent. There's both first order and higher order metrics that can be calculated, and which families were produced in different centers happen to vary. So it's when you have the GLDM metrics versus the GLCM metrics, if you don't have those 2 in common on different spots, you can't compare that across different centers. So with the radiomics workflow, as the field was expanding, the biggest challenge was this section. When radiomic features were calculated, this was not standardized. So IBSI, or the International Biomarker Standardization Initiative, came in to just kind of be our radiomic dictionary. What are we doing? What language are we speaking? What do each of these values mean? So they can be defined clearly, both mathematically and in plain English. So this set of definitions was published in 2020, and there's been multiple software packages that have resulted from that. So with these clear formulas and labels, we're now speaking the same language, trying to see what data we are processing, and the aggregating methods especially were clarified. So when I'm talking about aggregating methods, we have 2D, 2.5D, and 3D. So when we're taking this 3D data, when we're slicing it, when we're merging it, and when we're averaging these calculated features, there can be upwards of a 200% difference in the same statistic. So just making sure that when we are making these comparisons, it's apples to apples, not apples to oranges. Making sure that we are clearly defining and clearing up some of the confusion on the processing side. So image features themselves, there are 8 subgroups that are included in the IBSI package. There's the intensity, the histogram, and others, both our first order and our higher order metrics. These were all included in the IBSI package to describe various parts of image texture and varying intensity values. So with this, we have nearly 500 unique image features that are generated with IBSI. Which, with these clear definitions, we also have a digital phantom with that publication in order to validate other tools. This allows for that consistent basis of comparison, and one of the reasons we're at this conference is that we wanted to show our software package. IBSI was the set of definitions that was set out in 2020, and since then there have been Python-based approaches, there have been other MATLAB approaches. Our lab came up with a MATLAB and Octave-based implementation, and we're releasing that to the public for greater adoption of this set of statistics. So after generating this tool and validating it with the digital phantom or the mock-up image, making sure that our processing algorithm was accurate, we wanted to levy this tool to better clarify our workflow. So especially since we're working in a CT lab, something we wanted to look into was the scan reconstruction. So when we're trying to generate these models and figure out these radiomic baselines, there's a problem in that radiology has been a qualitative field for a long time, and most of the engineering tools that have been generated have been focused on clarifying the individual images. We're trying to engineer better scanners. We're trying to create finer details so a radiologist can look at it clearer. But those filters that are applied and those processing techniques obfuscate that raw data. We can't send over all of the 1D line integrals from a CT reconstruction. So with these variations in reconstruction, that essentially corrupts the data we're looking at. So trying to figure out what these reconstruction differences are and how to account for them in our models so that we are assessing biological difference rather than mathematical difference was one of our goals with this recent project. So a little bit more about computed tomography, or CT. Over 75 million of these are taken a year in the US. That is a lot of data, which can be levied in the future, but it's where safe levels of ionizing radiation pass through a patient and hit the scanner on the opposite side. We wanted to start with CT especially because with the way that this is created, there's something called a Hounsfield unit, which is relative to density, because as the ionizing radiation passes through a patient, the signal attenuation correlates with the density. So there is a physical component to CT, and there is a baseline. The Hounsfield unit of 0 is if it passes through pure water, negative 1,000 is pure air. So it has a physical component and is less mathematically sticky than MR. So starting with this, knowing we kind of have this ground truth of, okay, density and the pixel intensity are correlated with that signal attenuation. And then as all of these 1D signals are collected, a reconstruction algorithm is applied and then pops out the image we know and love that radiologists can use to make diagnoses. But something we found is with these reconstruction kernels, with these varying reconstruction algorithms, there is a difference that the radiomic data does pick up on. So these two scans are the same slice thickness, the same patient on the same day. And as the screen's a little far away, if you can see close up, there are these differences in the smoothness and sharpness of these kernels. These are the same raw data, but because of the difference in reconstruction algorithm, this messes with our radiomic data because it's an introduced difference that is not based on a biological difference. So what we're looking for is trying to characterize that data when it's proprietary information. Reconstruction kernels are specific to individual scanners and individual companies. So we wanted to see, when we use this radiomic data, make sure to account for this difference and remove that difference. And the reconstruction kernel specifically, there's 58 different ones at Toshiba. The Toshiba CT scanner we used, with those 58 differences, it's all based on what window you're trying to view. So even though the Hounsfield unit is a unit of density, when you have those different windows, there's a bone window, there's a lung window, there's different densities of different tissues that you optimize your reconstruction kernel for, and that does present itself in the scan later on. So recently we wanted to show and characterize these differences and look into potential phase differences. And phase, when we're talking about 4D imaging with contrast, there's the arterial and venous phases. So as that contrast passes through a patient's body, the brightness changes. And we wanted to see how this affects our radiomic data and what the potential differences are. So we took one patient scan on one day. We had a consistent slice thickness. We took 2 contrast phases. We took a complex cyst renal scan, and we reconstructed the data in all 58 kernels. We also generated all radiomic values, and by controlling for all of these other sources of variation, we were looking specifically for the differences in the mathematical differences there, and minimize the clinical noise and the clinical variation that is possible. So after generating these 250,000 data points, how are we going to look at this in a meaningful way? So the way we did that was generating 2 sets of heat maps. So set 1 was to characterize the interkernel variation. So ideally, there is no change. All the radiomic data popped out at that same kernel should mathematically be equivalent if there wasn't a difference because of the image kernels. We wanted to summarize the data from the different ROIs we took. ROIs for us are region of interest. We are not business people. This is just ROI for imaging, and we took the standard deviation of all the values of that one image feature, of those 463 descriptive statistics specifically for medical imaging. And then the goal was to see how and if these image feature values change because of the image kernels. So what could be throwing off our future models? What are the differences we need to account for and control for when we're trying to apply these clinically? So the second set was to characterize individual kernels, whether we could omit or include specific kernels that are more robust to these kernel differences. We were trying to see when there's variation where it is. So we have the 2 heat maps from the 2 different phases, and then 10 heat maps when we were trying to look at each of the different kernels. So we took the z-score to see kind of where our outliers were, just to look at the distribution and see which were the furthest off from that mean. And then it was supposed to see the distribution of image features relative to the kernel number. So this was the first set of heat maps we generated. We were trying to look, let me walk you through. This is our y-axis, which is the number of the image feature. On the other y-axis, we have the different feature families. So these are 8 different subgroups that we used for the different intermediate calculations, and then our first order statistics on the bottom. Our x-axis is our ROI with the complex cyst, the fat, liver, muscle, and spleen. And these are the 2 different phases. A lighter intensity, your white values have a much lower standard deviation. Your more intense values, your purple values, are a high standard deviation, which means that these statistics specifically varied a lot across the image kernels. So looking at this, we can say that there is a mathematical difference posed by the image kernels. If there wasn't, this would be nothing but white. However, all of the standard deviations are shown and summarized here. I wanted to highlight some of the families that had lower standard deviations with this set of calculations. So the GLDZM and the GLCM especially had particularly low intensity values. And this means that in future models, when we cannot control for image kernels, using this set of statistics is potentially more helpful when we're trying to discern simply the biological difference and not the mathematical difference. The GLCM as well, except for this repeating line, which is actually the autocorrelation. So we can tell that the autocorrelation is picking up on those kernel differences, and the others are not. So seeing this, which ones are egregious offenders, which ones are changing widely with the difference in image kernels. Those are your GLSCM and NGTDM features. We wanted to thoroughly characterize this whole image set to see where our differences were, and these two subgroups had particularly high differences. So jumping into our next set of heat maps, we wanted to see which of these kernels had those differences. We know that there's a difference across the image kernels, but which ones were potentially the cause of that. So this is one of our ROIs and one of our phases. And as you can see, kernel 31 and kernel 60 of this data set had the highest number of outliers. These are contributing greatly to those differences, and omitting these in future studies could help control for those differences that we're not looking to have. Especially with these high intensity values, it's clear that upon a visual inspection that this is data with more outliers and it's not close to the mean value of these generated statistics. And even you can see there isn't a clear trend across the image kernels. It's while these image kernels are numbered, it's not a direct gradation. It's not one fine-tuned parameter in these reconstruction filters. It seems fairly random. There's variation in between the kernels and in between the statistics themselves. So we generated 10. It's what these are all here for, is to show that we had the same differences in FC60 and FC31 across the different heat maps. And ultimately, kernels are proprietary information. We're unaware of exactly what math goes behind these 2D scans, and we can see that it does affect the radiomics we're trying to calculate. There's no clear trend because this varies metric to metric and it varies kernel to kernel. So because there is no trend, having a clear characterization of where these differences lie is important for informing future studies. And to make these quantifications consistent, we need to account for this difference, either through clearly communicating which kernels, which scanners we use, or from creating a harmonization algorithm later to account for these differences. So there's still a lot of work to be done in the scan reconstruction because this can affect our final tools and how we inform our radiologists. But in other ways, because this set of nearly 500 statistics is relatively new, it came out in 2020, we're trying to figure out what these baselines are. These are all quantitative descriptors of texture, but these have not been connected to qualitative descriptions of texture as of yet. So our second project with these tools that we generated was to look at the Brodat's textures. Has anyone here worked in image classification or image classification algorithms? Yep, definitely. It's your Rodax textures. It's a set of standardized textures. We're working with a little over 100 of these. They're a whole bunch of pictures of just every different texture under the sun, close up to see these kind of variations. And this was partially to test our algorithm, but we've seen in prior work that different tissue types do have different textures, and tumors have different texture types than regular tissue. So understanding the Brodat's textures before looking at clinical variation, before looking at multiple different patients, because even with one patient, you're never going to get exactly the same snapshot on exactly the same day. So looking at this, we're controlling for those different sources of clinical variation while just understanding the tools we're using a little bit better. And we wanted to use this because it's been used in the past to validate other image classification algorithms. And by prior work, it was sorted into general texture classifications. There were 3 different algorithms used, and study participant info also used to separate these 112 images into 7 different clusters. And with that, we have cluster 1. This is our first set of images that we were using. These were upon a qualitative assessment, lots of repeating lines. We have our cluster 2. These are more of your brick or your woven patterns. Cluster 3, more radial patterns, lots of wood. Cluster 4, these were more of your stones, your rocks, different things. These are all natural textures that we were trying to analyze with our data to see which of these qualitative texture differences our data was picking up on. Cluster 5, we have more of your discrete organic shapes. Cluster 6, these are more of the Brodat's textures. More of your rocks, more of your shales. And cluster 7, these were your really fine, coarse textures with lots of variation. So with these 7 different clusters, we have these representative images just to go back to and see, okay, when we have a large difference in our AUCs, when we have a quantitative difference, what is that qualitative difference? So for our statistical analysis for this, we threw all 112 Brodat's textures through our IBSI Radiomic package. With these different clusters as part of the labeling. We averaged the image feature value taken for each cluster. We took pair comparisons, which generated an AUC or area under the curve value. That's a metric we're using for comparing the similarities. And these were also sorted by feature and feature subgroup. And the ultimate goal was to identify which features distinguish between texture categories and which features were relatively consistent across similar texture categories. So this was the behemoth of a heat map we generated. As you can see, the lower intensities, those are our low AUCs to our high AUCs. It ranges between 0 and 1. On the bottom, we have our classifications. These were those comparisons of cluster 1, cluster 2, cluster 1, cluster 3, and so on. These are our features on the side, all 463, also organized by these different families. And we were looking for which clusters had the biggest differences. So cluster 1 versus cluster 4 were 2 of our biggest differences, and those were our really regular organized patterns versus our more rocks, other patterns. It's trying to build a bridge between that quantitative and qualitative assessment. So cluster 1 and cluster 4 were relatively high. All of the cluster 1 comparisons had relatively high AUCs. And moving through, just a reminder of what our clusters look like. And cluster 4 and cluster 7, cluster 5 and cluster 7. But something that was relatively consistent that didn't have much of a difference were our really fine gritty textures, with our more organized lined textures. And we were also looking just to see which feature families were the best at distinguishing between different textures. So what we found were the GL, RLM, and NGTDM. These were some of our higher order statistics were some of the best at distinguishing between these different texture types. So this is part of how we are establishing these baselines and trying to just inform these future models for having a quantified basis for texture. So jumping into just how the patient scans differ and how we're trying to use data informatics for our workflow, I will pass it back off.
So I hope you're getting a sort of a taste of like the complexity behind this and what we're trying to actually get out of this this quantification. It's not a simple one layer. You know, you process these images and then you can just compare them straight off. There's a lot of underlying differences in just the acquisition and the construction of these images before we even get a chance to start looking at them. And so, just to give you some ideas, there's a major issue with image non-linearity, and the problem being, let's see, is this playing?
It should play. We might need to go to the downloaded version. Ah, there we go.
Okay. That did not play. Well, I'll show you that video afterwards. Physiological motion. So when you breathe, organs move. And so if you think about your kidneys or your lungs, if you're trying to image those structures, when you're breathing, depending on what part of the breathing cycle you have, and when they're taking the image, your organs might be in completely different places. And so there's an element of image registration, and that image registration has to occur in 3 dimensions to compensate for it. There's distortion as you're breathing, so your liver flaps like a manta ray. And when that happens, you have to non-linearly warp that liver to fit a previous state so that you can do a comparison. So there's these physiological motions that you have to compensate for. In addition, let's see, come on. So in addition, there's artifacts of all different types, right? This is an example of what you would get if you had fillings or have braces while you're doing a CT scan. Metal artifacting on CT images is a big problem. And as we get more and more new implants, this has actually become a rather large issue in medical imaging. How do you compensate for these metal implants that cast issues? So what you're seeing there is an artifact of the reconstruction process. There isn't gleaming protrusions coming out of this person's mouth, but it looks like that on the images. Tissue boundary layers is a classic issue with MRI. So things like the sinuses have image warping capabilities for your MRI images, and so that's one of the major problems in brain imaging, is that these images become nonlinearly distorted because there's a tissue boundary layer, and that's just an artifact of the imaging process that is associated with MRIs. So again, lots of image setting differences, as in what are the differences of the actual acquisition parameters. So the field of view, how much are you looking at? What is the size of the person that you're imaging? How much detail are you getting into? The relative advancement of the imaging modality. For example, if you're using a 20-year-old scanner versus a 5-year-old scanner, the level of technology has increased, and therefore the image quality has probably increased also. And how do you compare these type of studies? So there are many challenges to us getting these medical images. First and foremost, in America we have something called HIPAA, which is spelled H-I-P-A-A, not H-I-P-P-A, as you might have seen somewhere out there. And what HIPAA says is that your your medical information is your medical information. We, as researchers, need to get approval to use your medical information. There are waivers that can occur if we keep everything anonymized and there is no additional burden to people, but it is something that, in terms of imaging studies, if we're doing prospective things, makes it a little bit more difficult. For example, we need IRB approval, or Institutional Review Board approval, for any prospective study where we're subjecting either normals or somebody with a condition to ionizing radiation, for example. So we have to justify why receiving that is either trivial or in terms of exposure, or there is some perceived benefit besides just the research. So it makes it a little bit more complicated. Healthcare systems are incredibly siloed. Has anybody here tried to go from one hospital to another? Ever? It's difficult in most cases. I'll put it that way. Your medical records are kept by each individual hospital unless you're with a large system. And even the large systems don't correspond to other large systems, okay? Notable exceptions, if you're a member, if you get your healthcare through the VA, they're all connected, which is kind of interesting. But pretty much everyone else is siloed to the point where following patients is very difficult, especially if you move and you change healthcare providers. And then finally, the data that we're getting, if we're talking about retrospective studies, using existing data, can come with a whole variety of issues. Even at one institution, one place of doing the scans, if you're dealing with multiple places doing the scan, they might have completely different protocols, different machines, different vendors. So how do you take into account of that? So these are some of the data challenges that we are dealing with. And then finally, we're talking about large data files. In the orders of gigabytes now, like hundreds of megabytes, 2 gigabytes. Not quite as large as pathology slides these days, but still a fair amount of information. And moving all that information has become an issue. And so one of the things that we're trying to apply is a lot of machine learning to radiology. And it's actually one of the brightest spots in terms of AI and machine learning and deep learning is the application to medicine, I believe. I think less controversial than generating videos of people saying things. The general outlook for machine learning, deep learning into medicine is positive in a lot of ways. In fact, the people that are most scared about it are the doctors that think they might get replaced one day. So what we've seen is that this has risen in many fields, and we're trying to adapt it to medicine. And the problem with imaging is it's all qualitative before last 20 years or so. It's all qualitative. We need to be able to turn that qualitative data into something that these systems, these technologies of big data technologies can process. And that's quantification of some sort, right? And radiomics is one of the many attempts to turn this data into something that we can then leverage a lot of this machine learning technology to start analyzing. And then finally, the problem is we are dealing with images that are mathematically reconstructed images of the human body, and then we're applying math to it to try to find something that separates these differences. And is all of this just a mathematical, anomaly that we're calculating? Is there any correlation to actual biology or physiological differences? And one of the things that we're looking at with the correlating to actual textures is once you get to the abstract layer of calculating metrics for textures and comparing individual values of these calculated things, does that really mean anything when you get back to the actual images that can be acted upon or that is physiologically related? Or are we just saying that through the benefits of math somewhere down the imaging pipeline on this one machine, we're able to detect differences between these two? And then we get into this entire black box argument of what are we actually looking at. One of the newer approaches, anybody here heard of federated learning? It's a concept that's gaining more attraction, especially in the medical field. What it basically means is instead of moving data and then processing it in some place, you actually can process the data in-house at the in the secure area, and then just send out the processed information for aggregation at a larger site level. So previously speaking, the way that you do medical imaging research is the people that needed the images, you kind of use a central repository, everybody sent the images there, and then somebody did the processing. And then they did, segmentation, and then they did analysis, and then they came out with we've done 5 different centers, this is the result. Well, so the federated learning approach is a little bit different. None of the data gets transferred. The data is processed in the places that you have. So you're using the same algorithms at all these different places. So you forego that entire issues with HIPAA and transferring data and making sure that you're anonymizing data. You do it in the areas that already have access. And then you submit the essentially anonymized group results into a central area, which then can be combined, and then further research can be done in that model. Or you can actually train your machines if you're doing machine learning, calculate your intermediate coefficients or variables or whatever, tuning algorithms, and then take that and feed it into the overall machine learning model at a later time, and then go back and individually test. So you basically don't have to send data around, and that gets around some of the unique healthcare challenges that we have here in America. So one of the other interesting things is that when we do it this way, we remove the need for PHI, which is private or personal health information or private health information, depending on who's using the acronym. And then, and so you can do these multi-center studies without actually moving data. So again, one of the other things is that a lot of other omics-driven data, like proteomics, genomics, epigenomics, they generate a lot of data also. And they generate a lot of quantitative data or labeled data. And now we're in the phase of taking a person's complete data in all these different fields and trying to figure out if there's signatures for example, disease states, or for growth factors or developmental differences. And this is very exciting because this is kind of the first time that we can actually look at people in this totality as opposed to just looking at one aspect of each of these patients. So we're trying to find now these multi-omic explanations for not only disease progression, but even developmental aspects, just looking at normal growth. And so one of the things that we're hoping that this, and it's a trend in radiology, is that quantification is becoming more and more pushed forward as a basic part of clinical work. And so, calculating the volume of a tumor has become now more standardized. And before, it was just calculating the diameter of a tumor and saying, oh, that's, 5 centimeters, we should probably take it out. Now it's calculating that this is actually, 200 milliliters. Let's see how big it gets or how small it gets with treatment. And so that extra level of precision can lead us into better diagnosis, better prognosis of diseases. And then finally, the harmonization aspects is important because what we're going to try to do is, this is not going to work at one center. And a lot of the papers that you read out there, that's the bias, is that they did it at one center, one population, might not have been genetically diverse, might not have had all the same, or might not have the same equipment as other places, and then that becomes the standard for everybody. Expanding this, larger data sets, larger participation equals hopefully better actual outcomes. And so let's just finish up. We are providing this IBSI compliant package. We're hoping that this will catalyze more research into reliable metrics. And this is also ideal in starting the talks of doing federated learning projects. And also, right now, the quantitative aspects doesn't really address all the issues with the data in general, but this is a starting point, right? And for those of you that are inclined and want to try it out, this is the link to our GitHub. Everything is open source right now, and you know, have fun. And with that, I think, yeah, that's it.
Thank you guys very much for your attention.
All right, great talk. So the technical issues are kind of squeezing the two talks together. So I want to see if we can get as many questions as possible in a short time. So while our speakers are answering one question, if you signal me, I will pre-position myself for the next one, and we'll see if we can get some good discussion here.
This is exciting, as I have trouble with my eyes, but what's really important is I noticed that like at Kaiser, they only keep the data around for a short period of time. So there's the only summary image is all they have after a period of time, and it seems that that even goes away at a period of time. So is there a possibility that the manufacturers will provide some level of software to support a higher resolution images, since they're for analysis versus images just to observe?
There's a bunch of medical legal issues with storing images. By law, if you get a scan, your hospital that is scanning that has to keep it for 7 years at a minimum. At my institution at USC, we actually don't delete any of the images. Now, one of the bigger problems is that how images are reconstructed is the resolution issue that you're talking about, because images are reconstructed specifically just for the viewing convenience of the radiologist. So higher resolution images, if you're reconstructing from the raw data isn't stored. And that's, there's many theories on that, but one of the issues is if you have data that isn't that can be reconstructed at a thinner slice, and then later on somebody sues you and you reconstruct that image, and then they can say, oh well, you can reconstruct that image, why didn't you reconstruct it at a thinner slice and catch it? And there's a bunch of medical legal issues with that. So my best guess is that vendors won't be doing that anytime soon. Individual institutions might institute a little bit more of that, but you as a person that is getting the scan, actually, if you want your own personal data, you have the opportunity to request a copy of all your images. So, you know, you yourself can be your own advocate and get that data, you know, proactively. So that's another avenue.
I have two questions.
Yes.
The first question is this mainly with just CTs and MRIs, like for me, because of something that I have to do every other year or so, is echocardiograms.
Okay.
So is this going to be applicable to that? Have you even gone that direction?
Well, so this is specifically for, it works for images, right? So this is made specifically for imaging. For the echo, is that more, that's more two-dimensional data, right? We're talking about waveforms on that, if I remember correctly, like EEGs or EKGs, right? Oh, okay. Oh, yeah. Okay, so if you're doing ejection fraction, actually, part of that is, these are things that can be applied to that. So, for example, like in terms of what we're saying about quantification, most of the time with ejection fraction, you're just measuring a volume, and you're trying to see the different volume at the different phase of the heart. And keeping track of that information now is becoming more and more prevalent at medical institutions, where they want to see if that expansion is done, or see how that progression is going. You can do this. The difficulty with standard images like that is this is probably more useful for disease states where it's kind of static, so like tumor analysis rather than a functional analysis. But we are doing work with structural differences, and that might actually lend itself to things like if you take the contrast inside the heart and see how that's shaped and how that changes shape, maybe that's something that we'll look at in the future.
All right. I think this may be our last question. We'll see how it goes.
Sure.
So obviously it's a challenge when you have like a lot of different medical device providers with a bunch of different data coming out of them. It's great that you have a standard. Is there much industry movement around either adopting IBSI or medical device providers having their own radiomics data for the use of creating like diagnostic models?
So not the device manufacturers, but actually the PACS vendors are starting to look at it. So the PACS is a picture archiving communication system. That's the viewer for the software. And so it'd be more of a post-processing analysis, not on the scanning side, but the afterwards, the viewing and processing side. So there are several vendors that are looking into adding these type of calculations into their systems. So for example, you can draw an ROI and it'll process it and it'll give you those values. But the question is, what do those values mean right now? So that's some of the studies that we have to do. It's particularly challenging in our current medical systems because we just don't have universal access to all the images. It kind of puts us behind other places like China, where all the images are essentially in one big central database, but there's quality issues with their data also and stuff like that. But I think as we go more and more quantitative, that's definitely the trend that is happening in medicine. We're trying to leverage these things because we know big data is where it's at. And the only way we're going to get to that is taking these images and doing something, quantitatively processing it, to get it to that state.
Okay, I think we'd better cut it off there. I'm sorry for the shorter question-answer period, but let's thank our speakers again, please. It's a great talk.